Hello, my name is Segerstrom. I am a PhD student at Rensselaer Polytechnic Institute, and today I will be discussing the parameter estimation and model validation of the Quanser AERO using Modelica and RaPId. I'll start by introducing the system that's modeled in this work, the Quanser AERO. Next, the multi-domain modeling approach used to develop the AERO model will be discussed, and then I'll introduce the RaPId toolbox, which was used to apply and automate the two optimization methods used in this work: particle swarm optimization and MathWorks fmin algorithm. Finally, I'll share some results from this work. So the Quanser AERO is a benchtop dual rotor system that can be reconfigured into several aerospace systems and simulations, including a 1 degree of freedom, single input, single output configuration for attitude control, as well as 2 degree of freedom, multiple input, multiple output configurations to simulate a helicopter or a half quad rotor. In this work, the 1 degree of freedom configuration shown on this slide was considered exclusively. The AERO contains several sensors for data measurement, including pitch and yaw axes encoders for measuring position and angle, as well as tachometers for measuring the speed of the motors. This diagram gives a top-level overview of the multi-domain model being optimized in this work. The model was developed in Dymola using the Modelica modeling language. Modelica allows for the implementation of models that have components from multiple engineering domains by defining equation-based interfaces between components that adhere to the principles and laws that govern those domains. The model developed for this work integrates electrical, mechanical, as well as aerodynamical components and interfaces to create a more complete picture of the system that's being modeled and its dynamics. Using the RaPId toolbox and output data measured from the AERO, we can improve the response of the model to more accurately reflect the behavior of the physical system by optimizing certain key parameters in the model. RaPId parameter identification, more commonly referred to by its acronym RaPId, is an open source modular toolbox developed in MATLAB and Simulink for automated model validation, calibration, and parameter estimation. It's compatible with multi-domain models developed in Modelica through the use of functional mockup units, or FMUs. An FMU is just a container that adheres to the functional mockup interface standard and contains a model that's compiled as C code that can be simulated as one cohesive unit in Simulink. Using Modelon's FMI toolbox or another FMI-compliant tool, FMUs can be imported into Simulink for simulation. The parameters and outputs of these FMUs can then be procedurally altered while in the simulation environment. The model on screen was developed in Simulink for use with RaPId. The FMU in the center contains the entire multi-domain model that we discussed previously. An input signal is provided to one of the model motors, and the resulting pitch angle output is compared to data measured from this physical system. So once a Simulink model that can be used with RaPId is established, the toolbox can iteratively determine an optimal set of parameters by minimizing the chosen cost function. This process begins by defining the simulation experiment. Vectors for initial parameter values, as well as lower and upper limits for these parameter values, are established by the user. Experiment settings, such as the path to the Simulink model in FMU, the cost function used to calculate error, a minimum error tolerance, an optimization algorithm, and a path to the measured reference data are also established by the user. Once all parameters, inputs, and outputs are defined, RaPId can begin its parameter optimization routine. First, a solution is found using the specified optimization algorithm and initial parameter values. The error is then calculated using the specified cost function to compare the simulation results to the measured reference data. If the error is below the user-defined error tolerance, the parameter set obtained is considered to be the optimized solution. If not, the next vector of parameters is used as the input for the next iteration of the experiment. With each iteration, the fitness of the model is calculated as the sum of the Frobenius norm of the error, epsilon, at each time step, as described by the cost function shown here. In this work, two optimization algorithms were compared for their efficacy at optimizing parameters for the Quanser AERO model. The first optimization algorithm utilized was a particle swarm optimization, or PSO algorithm. PSO is a population-based algorithm in which a collection of candidate solutions, or particles, are pseudo-randomly placed in a parameter space according to the bounds specified. With every iteration of the optimization routine, the cost function for each particle is evaluated, determining the new velocity of each particle to the next step. The goal of the PSO algorithm is to find a solution that's the global minimum. However, this is not necessarily a guaranteed outcome. The second optimization algorithm we used was a constrained nonlinear optimization algorithm included in MathWorks' optimization toolbox, known as fmincon. Fmincon attempts to find the local minimum of a problem specified by the first equation shown here. In this case, the error epsilon is defined as the absolute difference between the measured output and the simulated output calculated at each time step, according to the second equation. Since approximate parameter values for the arrow can be obtained from documentation from Quanser, it's not necessary to find a global solution. As such, the fmincon algorithm is expected to obtain more adequate results than the PSO algorithm and in less time. To evaluate these optimization algorithms, 6 parameters were optimized: the armature inductance and resistance of the motor, the rotor and stator inertia of the motor, and the aerodynamic drag and thrust coefficients of the arrow. The electrical parameters were optimized using the current through the motor as the measured output data, the mechanical parameters use the mechanical speed of the motor as the reference data, and the aerodynamical parameters were optimized using the pitch angle of the arrow body. For all experiments, the input signal provided a constant 24-volt input for 20 seconds before stepping down to 0 volts for an additional 20 seconds. After optimizing all 6 parameters with both optimization algorithms, the pitch angle of the optimized models were plotted with the corresponding output from the physical system, the unoptimized model, and a transfer function model that was provided by Quanser. As you can see, the first PSO optimized model was a poor representation of the system. The second PSO optimized model used the unoptimized electrical parameters instead and resulted in a much better representation of the system. It can also be qualitatively observed that while the second PSO optimized model tracks the measured reference output closer than the unoptimized and transfer function models, the fmincon optimized model is the best representation of the physical system. These observations are also reflected quantitatively in the fitness values for each model. A fitness value close to 0 indicates a low error between the measured and simulated output data, thereby indicating a model that accurately replicates the behavior of the physical system. As observed in the plot on the previous slide, the fmincon algorithm achieved the closest fit to the measured reference data. This indicates that an optimization algorithm that attempts to find a local solution is likely more appropriate for solutions where approximate parameter values are already known, rather than attempting to find a global minimum. Again, note that the first PSO optimized model includes the optimized electrical parameters and performs significantly worse than the unoptimized or even the transfer function models. By using the unoptimized electrical parameters, however, the second PSO optimized model performs slightly better than the unoptimized model. This might indicate a deficiency in the modeling of the electrical components in the multi-domain model of the arrow. As such, future work will address this issue and improve the accuracy of electrical component models to achieve better results from parameter optimization. The following are a few references to images that were used in this presentation. On behalf of my co-authors and I'd like to thank you for your time and enjoy the rest of your day. On behalf of my co-authors and I'd like to thank you for your time and enjoy the rest of your day. On behalf of my